I'm recording,
So,
by the way.
yeah. Sorry?
So I'm recording, so you can go ahead.
Okay, great. So basically, if you looked ahead a little bit in Diaconus, maybe you could kind of get a sense of why we would want to study this. But basically, the idea is that groups are fucking everywhere, or so does everyone know what a group is? Like, is that the kind of thing that people would like background on, or, but I mean, feel free to like message me in chat, or pipe up, or anything at all. If at any point you kind of like, or want me to slow down, want me to explain anything. But so groups are everywhere. Groups come up. They're one of the most fundamental objects in math, and honestly, like, we understand finite groups at this point pretty damn well. Like have classified. We basically know every single type of finite group. But for infinite groups, Lie groups, which come up in physics all the time, um, there are still things that we do not know about group theory, and it's so important, and it's so yeah, like it's extremely important. But there are still questions that we have. And on the other hand, linear algebra um, is also everywhere, but we really do understand linear algebra. And so representation theory is really just about like how do we make questions about groups into questions about matrices and vectors, because we know everything there is to know pretty much about matrices and vectors. And if you can turn something into a linear algebra problem, then the only thing left is like, well, how efficient is it to calculate? And so, um, and sure enough, like the fact that we can do this is just incredibly useful. Like it makes thinking about groups and thinking about symmetry um, just very, very like much easier. It's a really good way to like kind of think about the problem. And so this is kind of like the bones of it is what we're looking for is a matrix representation of a group. And so we're almost always going to denote that as rho, like the P looking Greek letter. And this is a map from the group G to the space of matrices of a vector over a vector space, the GLV, the general linear group. And this is a group homomorphism, which means that you know uh, like this map is going to respect the group product in in the vector space as a matrix product. So for this first line, for all G, H, and G, rho of GH. So on the left, rho of GH, that is like the group product, G times H. And then on the right, that's a matrix product, like those rho of G times rho of H. And from just honestly from this, we get all sorts of like good, like immediate knowledge, which is that like if this exists, if this map exists, then so every group has an identity element, then the identity element is always going to be the identity matrix for whatever vector space that we're working over. And then also like the every matrix, like every representation of every group element is going to be, if we want it to be, is going to be Hermitian. And so if it's like basically like the inverse element is always going to be the conjugate transpose of, whatever like matrix that we get. And so all automatically, like we're just getting like, these very nice calculational tools, for like doing stuff with the group. Does this all kind of make sense, or am I kind of going too fast? Okay, cool. I haven't done anything like this in a long time, so just bear with me, and yeah, please tell me if you have any questions or anything at all. So to start off really easy, every group has the trivial representation. So you just send every single element of the group to 1, and 1 times 1 is 1, and it's always going to respect like the group product. And this is not very useful, but it actually does end up being important that we keep the trivial representation in mind. I'm starting off. I'm just going to like show you some representations, like some concrete examples of representations, so you can kind of think. You can make this more concrete in your head. Next, like we need to start thinking of like an actual group, and so we're gonna look at S3, which is the symmetric group on 3 elements, and so the elements of the group are a permutation of 3 elements, and so like 3, 2, 1, that group, it acts on a list of 3 things on a 3-dimensional vector space, say, by it sends the one, it does it by flipping the order around. If it was in XYZ order, then 3, 2, 1 acting on that goes to ZYX. And so you can get a representation of this as a matrix by just permuting the basis vectors. And so you can literally think all right, so the 3rd basis vector has 1 in the 3rd place, and I just put that in the 1st place. And the 2nd basis vector doesn't change, and so it stays where it is. And then the 1st basis vector with 1 in the 1st place goes to the 3rd place. And then you can actually see that this acts on a 3-dimensional vector in the same way that in the same way that you would kind of want you would want the group element to act. And so this is kind of the regular representation. This is what you would think of. These are these are what you think of when you think of permutation matrices. Very, I don't know, very important. Going a little, sorry, is that a question? Going a little more in the mathy direction, there's and every group, so every group has the trivial representation, and every group also has a permutation representation. And this is on a vector space that has the same dimension as the order of the group. So S3 has 6 elements, and what you do is you associate each basis vector of the vector space with a single element of the group. And what you want is what this representation really represents is the group acting on itself. So what you want is, again, for our element 3, 2, 1, then the representation of 3, 2, 1 on the one, whatever basis vector is assigned to the identity, the representation of 3, 2, 1 should act on the identity basis vector by sending it to the 3, 2, 1 basis vector. And in the same way, the representation for each element should act on this vector space in the way that that element acts on the whole group. And so you end up getting a 6x6 permutation matrix. Does this all also kind of make sense? And not that you should be able to read what's going, really what's going on here, that permutation matrix shouldn't necessarily mean anything to you. But one, so this is a really important one because one, it's really connected to something called the group ring, and like thinking about the group ring is ends up really can be really important for the mathematics. You can like ask a lot of questions about group theory and representation theory, and like in general, about instead of thinking about the group, thinking about the group ring. But then also, what this should kind of be making you think about is that you can have the trivial representation, which is one dimensional. I showed you the regular representation, which is like maybe the most natural one because for like the symmetric group on 3 elements, it makes like it's the one that is most kind of intuitive in terms of like the action of the symmetric group. But then also like there's this permutation group, and so we have a one-dimensional representation, we have a 3-dimensional representation, and we have a 6-dimensional representation. And those are just kind of like off the top of our head. And then it turns out that actually, if you have 2 representations, you can make new ones. And so you can really have representations of essentially arbitrary dimension. And and in particular, like with the trivial representation, you can add a useless dimension, like a useless dimension. You could have a 100-dimensional representation that is just the trivial or like the regular representation, which is like permuting the first 3 basis vectors, and then 97 basis vectors that aren't doing anything. And and then in general, like, if you have a representation, so like this is just kind of a general problem, that we're like, okay, we have these representations, and we can think about, what the representations mean in terms of like what vector spaces that they're acting on. But it's not at all obvious, like, what but suddenly like now it seems like we're in this kind of crazy forest of representations. And is that me or we're in this crazy forest of representations, and it's like how do we kind of make sense of this? But thinking about the trivial representation is actually kind of our way out, is that what we want is to look for the core pieces of a representation where where there are no sub-representations, where there's no like, oh, just an extra trivial representation living there as well, but not really doing anything. And so that from there, like, it turns out, we're very lucky, those are the irreducible representations. Like, we actually can find these prime factors of representations that don't have any sub-representations, and we're like, we can make every single representation that we would like from the irreducible representations, and just by doing like the direct sum. And so any given representation that you have has like a block diagonal form where each block is made up of an irreducible representation. I don't actually really have any more slides, but I think, can people still see my screen and I switch to Diaconus?
Yes.
So let's make this a little bit bigger. So, okay, I'm surely someone has a question at this point.
I kind of do. So yes. First of all, thanks for the presentation.
Yeah.
I do have one objection. So you said at the beginning we really understand linear algebra. I do have
Oh,
one
okay.
one and a half objections to that, which
All
is
right.
we understand finite dimensional linear algebra. We understand,
Okay.
but as
Yes.
soon as you stoop in infinite dimensions, you're in functional analysis, and I think that's not as well understood. And I think that's the case where we'll end up with Lie algebras and so on. But
Sure.
even
Okay.
even
That's fair enough.
finite, you do have the evil stuff of non-normal matrices and operators, um,
Yeah.
which I would argue are not as well understood as we wished they were. But that's a minor nitpick.
Okay. Yeah.
Um, yeah,
That's that is fair. I will accept that. Accept that objection.
but I mean the comment about non-normal matrices is pretty much esoteric for most people, I guess. So it's not super important.
Yeah.
Maybe can you go back a bit to the group ring because you didn't really define it on the slides. I remember it from the reading, but I think it might be good to like
Yeah.
give a
So
more detailed explanation.
yeah. Well, so the group ring is pretty much this, and so if instead of if instead of these kind of vectors, you uh like if I replaced this slide with like, x1, e times e123 plus x2 times e231, just kind of replace those with like scalars in our field, then um, then the group ring is just that. It is sums of, like some scalar times the element of the group. And the way to think of that would be, basically polynomials in the group, where instead of like elements of the group, it would be, like the, e231 would be like x squared, and then plus x cubed, plus x to the fourth, plus x to the fifth, and you have like kind of a polynomial, like x to the something, in place of each group element, and so that creates a ring, and you add it in the way that you add polynomials, and then you multiply it also kind of in the way that you multiply polynomials, but so, you know, like three, 231 um, times 3231 ends up just being 9 times the identity element. So like, 231 times 231, 231 is its own inverse, and so if you square it and you get the identity element. And so this, I suppose yeah, I should have, this is easier to like, um, probably easier to like see visually, but like in the same way that like x squared times x to the third gives you x to the fifth, and so if you're multiplying polynomials, you like take all of the two terms that sum to x to the fifth and like kind of group them together, along with their scalar factors. You do the same thing except with the group multiplication, and so this creates a ring, and this ring is totally isomorphic to this matrix algebra. That multiplication that I just described of, which is also like convolution, is the same as doing matrix multiplication with this representation. And so you can, basically any uh, yeah, so any like polynomial, any element of the ring is like, a sum of these, is like like a sum of these matrices times, some scalar. And then convolution in that ring uh, is, matrix multiplication, of these, like of that representation. And then so like where we're going with this, with the irreducible representations, means that in that ring, that ring is semi-simple, and you can get those polynomials in this block diagonal form, where each block is only, like each subring is only acting on its pair. Um, and then even cooler for finite groups is that ring is also the same as any function from the group to whatever scalar field you have. And that's actually like directly related to the work that I've been doing in trying to understand like a neural network that groks the action, like the symmetric group, the multiplication of the symmetric group.
Pretty cool.
Yeah. Yeah, no, it's I'm um
What about ideals? What does that look like here?
so the ideals are um the ideals of this ring are precisely the irreducible representations. That is so that yeah, so
Yeah,
like
yeah,
as a ring, and this is kind of why like you can almost any question that you have about the group and like representation theory, you can make it about the group ring, and it's pretty much exactly the same. So the irreducible representations are the ideals, or two-sided ideals of this group ring, and so the sub rings, like the block diagonal matrices are just the whatever like the direct sum of the irreducible representations. It's a completely one-to-one correspondence. Um,
And I do have maybe another question. So at some point you
yeah.
mentioned that it's useful to like keep the trivial representation in mind. Is that partly for category theory reasons, or not at all?
I mean, I think it's important to keep. I mean, I think like I I think that it's important to keep these representations in mind, like kind of these three that I've talked about, um, to because I guess at least like in doing this work, I have sometimes struggled with you know r- disentangling how a group acts on itself within an individual representation, and what the representation kind of means in terms of acting on its vector space. And so like I kind of whenever I'm doing this work, I try to keep like these three representations in mind to like be very very clear in terms of um to not like kind of lose sight of that distinction, that as a representation like it's doing group theory stuff when you're just kind of multiplying the different matrices together, and it's closed under the multiplication, and so you're always sending one representation to like one element of the representation to another element of the representation. But um like um like it's also important to um, like think about how it's acting on the vector space. And yeah. Um,
So, I guess at least for the finite groups, the idea
mhm.
here is like there's some sort of bijection, right, between the actions of the groups and actually what the group is doing. Does that make
Sorry.
sense?
Um, so yes, or well, so if you have a group action that um if you have if you have a set that the group is acting on that can be thought of as a vector space in any sense of the word, then yes, like this is, like, so in terms of, yeah, like the group action, like then yes, there is a bijection. But I guess I'm not sure, I don't want to say for certain, because I don't know. Yeah, there might be kind of group actions or the group acting on something that might not necessarily correspond to a vector space. So I don't know. Maybe that doesn't answer
Yeah.
your question.
No, I think I get what you're saying. Thank you.
Uh,
I think we had another question.
yeah,
I don't know. I heard something, but
yeah. Sorry.
otherwise, I think I had one, but I forgot it. I tried to find it again.
No, no. I mean, it's all right. I'm feeling a little. I'm suddenly feeling a little like I underprepared. Like I wish I kind of had more to talk about with the characters, and or kind of more to show and like to dive into like exactly how you decompose the irreducible representations. Because I guess so. What questions do people have about like like the character theory and stuff like that, or
I did have one more question.
yeah,
Early
what's up?
on, I think you said you were working on neural networks, right?
Yeah.
Like, is there like a more concrete example you can give? Is say in terms of like a large language model or something where you like this is what the matrices are encoding and this is what the decomposition would look like in terms of the neural networks. Maybe that would be more familiar to the people in this group.
Um. So I don't think that. Um. Uh. I don't know. I don't know about in terms of like a large language model. Um.
Well, like just any neural network, right? Like even the most simplest example.
So
Yeah.
yeah, in
Um.
grokking, for example,
Sorry.
I think like the first grokking paper they were studying like basically a neural network trained to learn
Yeah.
some commands and
So let me um. So something that I have been working on is a so um so something that I have been working on is a um model to so I'm building on I'm building on this paper that I'm going to put in chat, um, where you have a model and you just give it, the you have it learn the action, like the multiplication table of the symmetric group, and so this is the paper that I'm building on, and uh, and so you just um, and so yeah, so this is similar. This in itself is building on the um, building on like kind of like some of the Neil Nanda's grokking work, um, and you have you have just an MLP learn the action of the symmetric group. You give it. So I was doing it for S5, which has 120 elements, so there's 14,400 different ways to multiply two elements of S5. And so, you just have it initialize the embed, the like each element of S5 with a random vector, and have it predict, give it two vector, and then give it like two elements of S5, and it doesn't know anything about the symmetric group, and it just needs to learn how the symmetric group works, like what the multiplication table looks like. And so one, even if you only give it 30%, 40%, of like all of the 14,400 like multiplications, then it will learn perfectly the entire symmetric group. And that paper, really well received. I think it just got accepted. But they didn't actually figure out, like, in the same way as the modular arithmetic like work, like exactly what the circuit is. But I have been able to kind of see really clearly that, if you look just at the irreducible representations of S5, then, they appear plain as day in in the weights of the, like, in the embedding, and kind of throughout the network. And so, like, you get this kind of random initialization where at the start you have this big mix of all of these different kind of irreps, but then as the training goes on, the model will only use one or two really, and so, like, in this kind of Fourier basis, the activations of the network are really sparse, and so, like, this is just one run. There is, you can kind of see more examples of this in the interpretability section, the SN circuits, the SN circuits thread, but the model actually learns this subgroup structure of S5, again, on its own. Like, we don't give it any information, but so this is actually for S6, where, so 2 1 1 1 1 is one of the irreducible representations. Like, the irreducible representations of the symmetric group are in one-to-one correspondence with partitions of n. So, like, 6, like 2 1 1 1 1 adds up to 6, and there are 11 different ways that you can have numbers that add up to 6, and so so this is one of them, and something that we have now seen in, like, S5 and S6 is that this particular representation, or irreducible representation, like, picks out cosets of Sn minus 1, and I don't know, does this all kind of make sense? Or and this is, like, ongoing work. Like, I also don't have, like, the precise circuit, but yeah, I would not be able to do this analysis without like, thinking about how these, like, without thinking about how to, you can represent groups in vector spaces and with matrices.
I think maybe to
Can you
motivate.
predict how sparse you can make your model from something like? Oh, sorry.
I'll go on.
I was just asking. I was about to ask if he can predict, like, how sparse he can compress these models, right? Like, can you make a prediction based on this kind of work?
So, mm, so it's not. This is less about So I'm not sure that it really has a lot of bearing on how sparse that you can make the models. I think it's kind of more related to uh, or like not in like a useful way where it's like, oh, I want to make the model smaller. You know, it is, what this is doing is kind of, or what I think, what kind of my hypothesis is that it's more relevant to what has kind of been called like superposition, where you will have, in a multi-layer perceptron, like this kind of polysemanticity, where one neuron will represent multiple things, and it really like makes interpretability a lot harder. And what I'm seeing is that like it's not like there are useless neurons and like useless dimensions in these models, but in a like on the contrary, like the weight decay, the regularization is pretty intense, and that's actually like that's kind of necessary for the grokking to happen. But more like if in this bigger space, where you take each neuron and instead of it being a scalar, you put it in an 11-dimensional space where you decompose it into a sum of an 11-dimensional vector, and there's one dimension per irreducible representation. Then in that basis, you and so sorry, let me and I have another picture to kind of explain, but in that basis, then it's sparse, and so it's less like, but that's like a much bigger space, and so it's not like useful in terms of like pruning the model or anything like that, but it is useful in terms of interpretability and like finding a space where every neuron is monosemantic. Does that make sense? And so this is like the full equation for the Fourier transform over S5.
Are you
Sorry,
are you trying to show something on your screen?
I am. Are you not?
I think you might be only showing your browser. So right now we're
Oh,
still, at least I'm still seeing the slides.
oh Jesus! I totally thought. I'm so sorry. I thought I was. Oh my God. Um, I thought
Okay, now I see
so.
the image.
Okay, yeah. Um, so yeah, so this is one way that this particular irreducible represent. Oh Jesus! Well, now I feel, now I feel dumb. This is one way that this irreducible representation picks out. So this is on S. This is for a model that was trained on S6, and uh, like uh, you know, this particular neuron, looks at double cosets of S5 within S6, and like has this very predictable kind of behavior with respect to the coset. And there is another irreducible representation which only picks out the Frobenius group of like this like very weird group, the Frobenius group of order 20, and yeah, and then sorry. So this is what I was meaning to show is like this is like the equation
Ooh.
for the Fourier transform. And this is this is honestly this is precisely what Diaconis kind of recommends doing. Like but basically like this is a Fourier transform, and so f hat is your Fourier transform, and it's a function of the irreducible representation. And so in this way, they kind of end up acting like frequencies in the normal Fourier transform. And but what this means is that if you apply the Fourier transform again, you get your function back. Like, so f, the original f, is just, the sum, the normalized sum of its Fourier transform in this way. And if instead of like kind of completing that sum, you take each individual component, then you get this thing on the bottom where you get a new vector that has like how much each each irreducible representation contributes to the function for that for any given value.
Yeah, neat stuff. Although I don't think you actually introduced the Fourier transform in your slides, so some people might be a bit lost. But yeah, that's very
Yeah.
cool.
Yeah, and then okay, and then what I meant to show you before as well is this, where like uh, at the end of at the end of training, like so this is a graph of the Fourier transform like over time as the model is learning, and 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 so like you start off at a kind of a random initialization, and it's just all a mess, and like there's no sparsity at all. And then as training goes on, one or maybe two of the irreducible representations just takes off, and you get to end up seeing this like sparsity and these kind of more interpretable weights. Um, but yeah,
Have you tried like different kinds of data? Like, do text data look like text data, and like video embeddings look like video embeddings? Like, is that something you've tried?
so something that we would like to work on or like to see is, um, for well, so we can only do this because we know to look for this, and so like we know how or we have a good sense of like how the we know that the model has to be representing the symmetric group like at some point, or in some way. Something that we would like to do is like look for these patterns in like a large language model that can like do if the large language model can permute the elements of a list, then it would be really interesting to see evidence of like the actual like some like a matrix representation of the symmetric group like in that in the weights of the large language model. I looked into it before, and honestly, the only language model that I could get to consistently accurately do the symmetric group was GPT-4. And we don't have the weights and can't look at GPT-4.
Oh
So,
yeah, yeah, yeah. It's a bit of
so
a
so
problem.
that yeah, so that was definitely like a small problem. Um, but yeah, this is part of what I've been working on, and yeah, so I'm out. Yeah.
It's definitely very interesting.
All right, thank you. I appreciate that, and yeah, I don't know.
I may have one or more question, but does anyone else have questions at this point?
Yeah.
Yeah, I was. This is really cool. I think I sort of maybe see the connection to like the progress measures grokking paper now with like the Fourier basis.
Yeah.
I was wondering, I was curious, like, do you think that so like I think I'd need to read the toy model of universality paper better to remember this, but like there's they have just like two specialized like embedding layers, right, for like the input. And I'm
Hmm.
curious like what the input format is to your network that you're training to grok, and like do you think it
Yeah.
would be possible to take a language model and like give it this data in textual format and see if there's some sort of grokking possible?
Yeah. No, I mean, So the input format is just as like embedding vectors, and I had I thought I had toy model of, oh yeah. Um, so the input format is just as embedding vectors. I am really curious as well to, I mean, to kind of expand the input format. Um, but know, one, because like, just to see like how like what sort of different circuits form like when it is like a group action and not just kind of the group multiplication, and that would be more directly relevant to like once we have that understanding, like where if it was like we have an embedding vector for essentially like a token, that corresponds to each permutation, and then also like a list of 5 things, and like having a multiplication where the model learns to produce the permuted list, um, then that would be like more that would be directly relevant to like what a large language model does. And then if we can kind of find a way to get a large language model, or like find a large language model that does that like does this reliably, at like, and again, I didn't try, I tried a little bit. I spent like an afternoon trying to do like prompt tuning and like with different amounts of like in context, examples to give it. And yeah, I just didn't have a lot of success. But I definitely could try harder. But yeah, like taking this and like, seeing how, yeah, like how a model like represents a group action, and like, something like this, acting on a list or something along those lines would be, yeah, that's precisely where we want to take it.
So yeah, this is super, super interesting. Thank you.
Yeah. Yeah, we still don't. Something I am still extremely curious about is so like if so this like what you're seeing now, like this on the x-axis, this is like the number of epochs. But if you switch it to being about the loss, having the um uh like where what am I looking at? Um, if you switch the x-axis to being like the loss, then so this is this is only going from, this is like once it has already like really started to go down, but like this is like when it's on a like it's very like, this is it's log linear, like this kind of increase of like a single representation being used by the network. Like it's something that happens at the end of grokking, and it happens really quickly. Um, but uh, but it's something. It's definitely like this kind of sparsification is something that happens at the end. Something that I am still burning with curiosity about and have really kind of no clue about is why the test loss starts going down at all. Just like kind of the very basic fact of grokking, of like why the network can generalize from like 30% of the data to the whole data set. Like I don't think anyone knows. I don't think we've seen anyone, like people have kind of made hypotheses, but no one, no one knows at all. And so, but yeah, it's definitely, I've been really excited to work on this, and there's lots of questions. And if you'd like to work on this with me, right now it's pretty much just me doing this. But yeah, there's lots to do, and it is pretty exciting, and you get to think about representation theory, which is very cool.
Is this
Um,
last thing you mentioned related to mode collapsing?
I don't know. I don't know. I don't think so, but I don't know.
Okay. Sounded vaguely familiar.
Yeah, I mean, it's, if you're not familiar with grokking, it's you know, it is very related to like double descent, which is something that has kind of been in the air for a while.
Right.
Um, and I think people have shown pretty conclusively that it's very related to like double descent, and it's intimately related to kind of this fundamental question of like why do neural networks generalize so well? Because I mean, and I guess for me, like my training is in math, and I spent a lot of time studying statistics, and then I worked for a while as like a data scientist and like crunching numbers and building statistical models of like business things, and I don't know, like in your training as a statistician, you just learn like you can't really do better than the data that you have. That like if you think that you're doing better than the data that you have, it's probably because you've overfit, and that's really bad. And so this stuff with grokking, where it's like, no, actually overfitting is good. With neural networks that are way bigger than their data, overfitting is really good, and it will generalize. It will actually learn. It will learn stuff that is not in the data that you have. It will learn the structure of all of the data. That absolutely fucking blows my mind. That breaks all of the rules of statistics. That should not be how this works. And and yeah, I don't know. I just think that's cool, and I think it's at the core of so many of these questions, where if you asked someone 15 years ago, like, oh, could a language model that is just auto-regressively predicting the next token, do, and you describe like 5 things that GPT-2 can do, let alone GPT-3 or 4, they would have been like, absolutely fucking not. Like that, task is too dumb. There's not enough in the data to like support that kind of capability. And so like the fact of neural network generalization is, I mean, it's why we're all here. It's why it's why all of this exciting work is being done. But we still don't really understand how or why neural networks can do better than the data that they're given. And I think this is like the reason I like this is because it's just about the simplest. The simplest is like the modular arithmetic, but this is one step up from the simplest example that we can come up with, where you see this just extremely shocking behavior, like this behavior that breaks all of the rules of like statistical learning theory.
Okay. I think Nat, you may have a question.
Yeah, this is super cool work. Have you tried training a network that actually has an um, inductive bias for this group? So like a group equivariant network,
Sorry.
like a group equivariant network.
So I haven't tried training, I haven't tried building group equivariance into this. I mean, one way to look at this is how, like that, in a sense, like giving the network group equivariance would be cheating because you would be telling the network what to learn, in a very precise way. Like, and I actually only realized this like last week when I was kind of like trying to like sift through the math. But in a really precise way, you can cast this problem as group equivariance getting learned. And in the
Yes,
same way,
yes. Uh,
yeah,
The next
yeah.
question I was going to ask is, so once you did implement that, try to modify the method so you learn the actual group.
Yeah, yeah. I mean, so, or wait, sorry. Can you repeat that one more time? I'm being very dumb.
So like, do you think it would be possible to somehow use the insights we get from studying rocking to um, give networks the ability to learn group equivariances more easily without all this long training?
Yeah, I think I certainly hope so. I mean, I think like um, my hopes. like I and so because we already see in like vision transformers, um and like these kind of and frankly in convolutional neural networks that are not built in to be equivariant to like rotations and stuff, like we see that these things get learned. We know that this kind of like yeah, this equivariance, this like G linearity, where like the action of the group is linear in the vector space that we're like whatever vector space we're working with. We see that it does, like a convolutional neural network, like doesn't need to get like it realizes from its data that like if I rotate this cat, it is still a cat, and so it has this kind of it like learns the equivariance, um, and I do like hope that in by looking at this and seeing how those circuits um, how those circuits form, that we can kind of like take those insights and you know um, and see it happening in bigger models. Maybe make it more efficient in bigger models. But I mean, I guess my real hopes are mostly in terms of interpretability, where like I'm hoping that we can like the place where I really would like to go kind of once that this is all done is like so you can do a Fourier transform on groups, but you can also do Fourier transforms on you can do a Fourier transform on finite groups. You can also do it on infinite groups. You can do it on lots of different types of algebras, like particularly Hopf algebras and stuff like that. If you have as Stella keeps on telling me, like you can do it like the Fourier transform is really about measures. You can do it on like fractals, but like I am hopeful that with kind of what we're learning from this kind of simplified setting, we can kind of level it up and look for ways to decompose, like based on the data, really, but look for ways to decompose what a network has learned and like find a way to actually be able to interpret it. But yeah, that's just the hope, and that's definitely kind of further down the line. But yeah, like my hope is that for just kind of broader purposes that we'll be able to like um, look in kind of the frequency space for a bigger network. Yeah.
Okay. So yeah, that actually stole the question I was about to ask. So does anyone have any other question before we end? I guess not. So yeah, thank you very much, Dashiell, for the
Yeah.
presentation.
Well,
It was very interesting.
yeah. Thank you, and yeah, thanks everyone for being here and for your patience with me. And I'll um, what I guess would it be? Do people want to talk about um, what to kind of do and what to cover maybe for a session next week here, or should we just have that discussion in chat?
I think I'd at least be interested in more on the character theory. Like also if
Yeah,
you have more time to read it, but I don't know how other people feel.
yeah, we can do the character theory, and then I think also if people are interested, I can focus like introduce the Fourier transform more, in a better way, and that would and that and basically we can kind of stick with Diaconus and uh, yeah, and yeah, like because the characters, the character theory is absolutely essential for understanding the Fourier transform. You know, um,
Yeah, I think that sounds good. Maybe so next week we should do that. Oh, I think Haley had was about to say something. Sorry.
Oh yeah, no, I was just gonna say that sounds awesome. That would be.
Okay, cool.
Then
Yeah,
yeah,
let's do
should
it.
we do that for next week?
Yeah, I'm down with that.
All right. Well, yeah. Thanks so much, everyone. I really appreciate like your bearing with me as I. But yeah, really, and I really appreciate everyone being here.
Okay, thank you everybody. So let's end it for today and see you guys all next week.